Hello everyone, today we're going to talk about linear translation-invariant models and convolution. The prerequisites for this material are linear regression, Fourier series, and discrete Fourier transform. We're going to consider inverse problems where we want to estimate a signal y from noisy data x, where the noisy data have dimensionality n, so there are n entries each time we observe an example of the noisy data. And what we want to estimate is a signal y that also has n entries. So if you want, you can think of x and some noisy image, for example, and we want to estimate a clean image from that noisy image. Okay, so we already looked at problems like this when we introduced thresholding using wavelets or the short time Fourier transform to do denoising. So if we take a step back, this is very similar to the regression problem with an important difference. The important difference is that in the regression problem that we considered, we had these features. Well, believe it or not, I was attempting to draw a rectangle. So we had the features x, and we wanted to estimate a response y. Okay, this is what we wanted to do when we were looking at the regression problem. Here, instead, we're going to try to estimate a whole signal y that also has dimension n like x. I mean, the dimension could be slightly different. It doesn't have to be exactly n, but the point is that we also try to estimate a high-dimensional object. So it is a multivariate regression problem. And from that point of view, just like we discussed for the univariate regression problem, the best thing you can do from a mean square perspective, if you model x and y probabilistically, so that they have a joint distribution, the best thing that you can do is you can say, okay, for every value of x, my estimate is just going to be the mean of y conditioned on that value of x. Okay? The important part, of course, is that you're conditioning on that particular value of x. This is the best you can do from a mean squared error perspective, and the proof is exactly the same as in the univariate case. The thing is that we already discussed that this is actually impossible to do in the univariate case. So maybe give yourself a moment to remember why. And the reason is the curse of dimensionality. Okay, so are we done here? We're really not done here, because we cannot just estimate the conditional mean from data when the dimensionality of x is not ridiculously small. Okay, why? Because there's going to be many possible values that x can take. So imagine that x has just 20 entries and each of the entries has 2 possible values. Then we can encounter 2 to the 20 different values for the vector x. We're not going to be able to learn this from data. And usually the dimensionality is way beyond 20 and you don't have only 2 possible values. Okay, so because of the curse of dimensionality, you cannot use data to just learn a conditional mean and go on your merry way. That just is not going to work. So that's why we consider linear models. Of course, as we discussed, there's alternatives to linear models, and we will talk about nonlinear models a bit later on. But we could think, okay, we've seen that linear estimation actually works pretty well for some problems involving regression, so why don't we do linear estimation here? So the idea again would be to estimate the signal y from the noisy data x, and we would learn some linear function mapping x to y using least squares, just like we did in linear regression. Okay, so let's see. That would mean that I'm going to draw a picture here to hopefully make things a bit clearer. So again, remember we have x. Okay, that is a vector of dimension n. And we have y, which is another vector of dimension n. Okay, in this case, y has turned out to be more beautiful than x. So if we have a linear model, how many parameters, and these guys are in each dimension n, what is the dimensionality of the linear model? Again, pause the video. When I ask these kind of questions, I suggest you just pause the video and think a little bit about it. So basically the linear model, if we have actually, let me draw it in a bit more. The linear model, okay, like what's the dimensionality of this matrix remember that any linear transformation can be represented as a matrix. Well, the linear model is basically n by n, which means that the number of parameters of this linear model is what? It's n squared. Okay? So what is the difference with linear regression? The difference with linear regression is that in linear regression, univariate regression, I should say, wow, that was supposed to be a rectangle. In univariate regression, we have x, but y, crucially, is just a single number. Oops, sorry, let me make that into a beautiful square. So y is a single number. That means that for the univariate regression problem, the number of parameters is equal to what? Think about it. The number of parameters is just n. So it's not that bad. You can still do it. Okay, so this is the difference between the multivariate problem where you have an inverse problem where you have to estimate a whole image out of another image, and this univariate regression problem where you don't. Okay, here linear regression is still kind of tractable. Here we have to learn a model. On the left, I mean, we have to learn a model that has that has n squared parameters. When we're talking about images, n is typically at least 10 to the 4. So this would be 100 by 100 pixels. That's a really small image. You can have images that are 1,000 by 1,000. So n could easily be 1 million. For audio, you get to 1 million really quickly because as we discussed when we were discussing about the sampling rate and so on, you want to sample your audio at least at 40 kilohertz. So when you have like a 3-minute song, it's already going to be like 1 million samples. Okay, so n is really, really large. That means that if you are, let me maybe erase we have made our point, I believe, with this univariate regression thing. Like if you want to estimate, like this, if you want to fit this model that has n squared parameters, well, you're going to need a lot of data just to estimate a linear model, because if n is around 1 million, then your model has 10 to the 12 parameters. That is quite crazy. There are models that we fit when we fit deep neural networks and so on that have 10 to the 12 parameters, but they're not just simple linear models. It's a little bit crazy to fit a linear model that is so huge, and it's going to be very, very difficult. Okay, so the intuition here is that perhaps we should introduce some more assumptions, because if you realize here what we're saying is this linear model, what does it say? I think it's important to just stop for a moment and think about this. So for a certain pixel of the image or entry of this signal that we want to estimate, we are learning how all of the other pixels should be weighted. So each of these guys, okay, weight one of these pixels in the noisy image. And the thing is that probably you don't need all the noisy pixels in the image to estimate just this guy. You probably maybe just need the ones that are closer by, or the relevant ones in some sense. And maybe these weights here do not have to be different from each pixel. Maybe as we move around the image, you might want to use similar weights for similar pixels. Okay, so there's a lot of structure that we wouldn't be exploiting with this simple linear model. And in any case, because the number of parameters is so enormous, we just need to enforce additional assumptions in order to obtain a tractable model. And here, what we're going to consider is a very natural assumption, which is translation invariance. The idea is that if I have a noisy input that I'm processing, that would be x, and I shift it, then the estimate produced by my model, a reasonable assumption would be that it would just be a shifted estimate. So I realized that I said that pretty badly. What I mean is, so if you have x that corresponds to y. So your model maps x to y. If I shift x, we will describe this notation in a moment, but if I shift x by, let's say, 10 pixels to the right, my estimate should just be the same thing shifted 10 pixels to the right. Okay, these are quite natural assumption for quite a lot of different data types. So if you think of a song, like if you have a noisy recording and you just shift it, it's quite natural to ask from your estimation algorithm to just produce the same output but shifted. And same with images. That is called translation invariance, and it's a very powerful assumption. As we will see, in fact, it's the assumption that underlies the design of convolutional neural networks. Okay, so in order to study this assumption, we're going to introduce circular translation. I want to emphasize here that the fact that we're dealing with circular translations that wrap around, is not a big deal. This is just so that the math works out in a simple way. In practice, you probably don't want the translations to wrap around when you translate a signal like an audio signal or an image. You probably don't want it to appear on the other side, but that doesn't matter. Basically, those are border effects that you will deal with when you have to process real data. Usually what you can do is you can either pad with zeros or do some mirroring, or I mean, it gets a little bit complicated and annoying, but you deal with the border effects. Here we want to understand the fundamental reasoning, and for that we're going to just ignore border effects. We're going to assume that the circular translations are a reasonable thing to do, and just focus on the main ideas. So we're going to denote a translation by S, a shift of S entries by X with this little arrow looking down beside the next. Okay, and that just means that now the jth entry of the shifted signal is the j minus S entry of the original signal mod n, because we wrap around. But again, this wrapping around is not a big deal. This is just to make things simple from the mathematical point of view. Great. So now we're going to consider linear translation invariant functions or linear translation invariant models. We have already discussed what linear models look like. Basically, a function is linear if when you input, if you apply the function to a sum of inputs, that's just equal to the sum of the corresponding outputs. If you scale an input, that's just equal to a scaling the corresponding output. Okay. Now, when we have a function that is translation invariant, if we shift the input, then just that produces exactly the same output but shifted. Okay, just as I was saying, you have some noisy audio, you shift it by 10, your linear translation invariant function is going to produce the same output shifted by 10. Okay. So now we're going to think about how to parameterize linear translation invariant function or a linear translation invariant model. So think about, the comparison here is with just linear models or linear functions. Linear models or functions are just parameterized using a matrix. If you're mapping a vector n to another vector of dimension n to another vector of dimension n, the matrix is n by n. Now the question is, if I restrict my function to be translation invariant, now how do I parameterize it? Okay, so the idea here is that we have y and we're applying fl, which is a linear translation invariant function, to any vector x. And now here we're going to apply a trick, which is we're going to express x in terms of the standard basis. Okay, so just to be clear, basically here what we're saying is that x is equal to its first entry by a vector that is times a vector that is 1 in the first entry and zeros in the remaining entries, plus its second entry times a vector that is 0 everywhere except in its second entry, and so on and so forth. Okay, So just to be clear, this would be E1, E2, and so on. And now we're assuming linearity and translation invariance. Okay? So when you apply the function to all of this, it's exactly equivalent to applying it to each of these guys and then weighting them by x1, x2, and so on. Okay, so this is what this is saying. You just apply the function to each standard basis vector and you weight it by the entry of the vector. This is exactly how you prove that any linear function can be parameterized using a matrix. Okay, because the matrix essentially is going to have columns that correspond to the action of the function on each of the standard basis vectors. But here we're going to go a step further. The idea here is that if we're applying the function to this guy, the output should be exactly the same as if we apply to this guy, because the function is translation invariant, but shifted by 1. So when we apply the function to the jth standard basis vector, this is exactly the same as applying it to the 0th basis vector. Here we're numbering the signal from 0 to n-1. So maybe I will fix this. This would be e of 0, x of 0, because we're starting numbering at 0, then x of 1, e of 1, and so on. Okay, so this is exactly the same as applying the function to the first basis vector and then shifting, okay, because you can write ej as a shift of e0. Then by translation invariance we have this equality. So this, the function applied to, just to be clear, this is f of 0, 0, 0, 1, 0, 0, 0. By translation invariance, this is the same as applying the function to the vector 1, 1, 0, 0, 0, and then shifting this by j. The cool thing is that, if you realize, the only thing we need to compute to be able to apply this function is this. Well, this is a terrible color to highlight with. I'll use this one. Okay, the only thing we need is the function applied to a vector that is 1 in its first entries and 0 in the rest of the entries. And with that, you can just build everything else. Okay, you can just shift it to determine how the function is going to affect any other standard basis vectors, and then you just need to weight by the corresponding entry in the input vector. Okay, so we're going to call the function applied to that, the function applied to the standard basis vector that has a 1 in the first entry and 0 in the remaining entries, we're going to call that h, and h is all we need. In order to compute the function applied to any arbitrary vector x, the only thing we need is to know what this h is, and then we shift that and we weight it by the entries of the input signal, and that's it. And h, by the way, has dimensionality n. So this shows you that you can parameterize any linear translation invariant function or model with a vector of dimension n, and this is a very big deal, because if it's just an arbitrary linear function, then the dimensionality is n squared, which often makes it intractable or requires an enormous amount of data to not overfit. So usually these standard basis vectors that are like 0, 1, 0, 0, 0, 0, these are called impulse responses in the signal processing literature. Sorry, impulses in the, I got ahead of myself there. In the signal processing literature, when we look at what happens if we apply a function to them, the result of applying a function to them is called an impulse response. And what we have seen is that the impulse response obtained from the impulse that just has a 1 in the first entry and zeros elsewhere, that is sufficient to parameterize any linear translation invariant system, any linear translation invariant model. The reason I said linear translation invariant system is that I'm an electrical engineer, and these functions, these linear translation invariant functions, they're usually called systems in that literature. Okay, the idea is that if we have y and x, the only thing we need to do is take h, shift it, and then weight it by the entries of x, and that is going to give us any entry of y. this is called a convolution. Okay, and that's how convolutions, that's my favorite way of motivating convolutions. You assume translation invariance, and then you realize that applying a linear function that is also translation invariant just results in a convolution. So I've already given this away, but it's good to emphasize it. The number of parameters, if the signal and the data are both n-dimensional, is now no longer n squared. It's just the dimensionality, the dimension of I of h, which is equal to n. Okay? So we have really reduced the dimensionality of our model dramatically by enforcing translation invariance. So as I said, when we take a vector, okay, when we take two vectors and we shift one of them and then weight it by the entries of the other one, that is called a convolution. It's a circular convolution because we're assuming circular shifts, and we'll see very soon why this is a very useful assumption. But in general, you could also define this with normal shifts, then you would just call it a convolution, and in that case you would have to deal with border effects in different ways if you want to apply the results that we're going to define here, which you usually want. Okay, so let's see an example here. Have a convolution of a signal x with another signal y. And now we can think of, to compute the result. So I'm going to draw a little cartoon of the result here. So the result, for example, here would correspond to, like if this is, I don't know, minus 20, basically. Here what you would do is you would take this guy and you would shift it to center it at minus 20. So this guy is has width 10, so it would look something like this. You would take the inner product between them, in this case this would be 0, and that would be the convolution. And then you would start shifting this guy. So for example, at 0, this would look something like this. They would be on top of each other and you would get another value. Okay, so as you see, as this is shifted, we expect to essentially have values that look kind of like this and then like that as the shift moves away. Okay, so I recommend that you compute this on your own, but the idea is that you take this guy, you put it on top. The reason why we're going to see something flat here is that for a while this guy is completely going to be on top of this other guy because this guy is narrower, and that's exactly what we see. Okay, I recommend that you try to compute it on your own at least once to see how you would compute, but basically the important thing to remember is that each of these points corresponds to this whole signal y inner product with a shifted version of x. Okay. You can also define circular convolutions. In that case, what you do is you do 2D shifts. You shift to the left or right and upwards or downwards, and it's basically the same idea. So imagine that you have this image x, and you're going to convolve it with this blurring with this blur filter y. This is actually what happens in cameras because of diffraction, depending on the lens. So you're not going to have arbitrary high resolution in cameras because of the lens. You're going to get a little bit of a blur, and that blur can be often modeled as a convolution. Here we're going to shift y instead of shifting x because it's just easier to see. So the idea is that in the output at this particular point is going to be this guy shifted, and it's going to be shifted to here. So we're going to have like this blur here, and when we take the inner product, it's going to essentially compute a local average of the pixels there, and that is actually going to blur the edges that we're seeing. Okay, so that's blurring. You might have heard of blurring in other contexts. So blurring can be well modeled as a convolution with a filter that looks like this that computes a local average. Okay, so why did we introduce convolutions? Because LTI functions can be expressed, any LTI function, as we said a moment ago, can be expressed as the convolution between the input. So we had derived this we can now write more cleanly as the convolution of x with the impulse response of that particular LTI function. So of course you need to still compute the impulse response. This is what you would fit if you're fitting a linear translation invariant model. You need to find that impulse response from data, and then you can apply it to new data. Okay. In the case of in 2D, we're not going to go through the derivations in detail here, but it's essentially the same idea. If you have a 2D linear translation invariant model, you can parameterize it in terms of an impulse response that essentially tells you how the linear translation invariant model reacts when you input a single impulse at the center of the image. Here I'm saying image because we have an n by n signal. Okay, so now we're going to analyze convolutions in terms of Fourier transformations. We'll see in a moment why that's a good idea. I mean, maybe the first time you encounter it, you might be surprised, but as we will see, it makes a lot of sense. And all of this analysis is relies on the following fact. If you have a sinusoid, okay, like a sinusoid, of course you would have it would be a complex sinusoid, but let's forget about that for a moment. If you shift it, if you shift this sinusoid, you will get something like this. Again, I'm drawing, as usual, I'm drawing real sinusoids, even though I want to actually talk about complex sinusoids, but it's exactly the same idea. So here what you should notice is that we're not modifying the frequency at all. We're only modifying the phase. Okay? So if you remember, when we modify the phase of a complex exponential, this is just the same as multiplying by a complex constant. Okay, so translating a sinusoid just modifies its phase. Because we're considering complex sinusoids, we just have this shift here. This shift can come out. By the way, the way the phase is modified does depend on the frequency. Maybe that's important to point out. But at the end of the day, you get exactly the same sinusoid with the same frequency k multiplied by a constant term. And we're going to use this very simple fact to analyze convolution in terms of Fourier transformation. Okay, so now we have we're going to see what happens when you translate a signal, what happens to it in the Fourier domain, because the reason is that when we apply convolutions, we're taking essentially inner product with translated signals. So first, we're going to understand if we have a signal x and we shift it by s to get another signal y, how does that affect its Fourier transform? Its DFT, because we're talking about discrete vectors. Okay, so the way it affects its DFT is the DFT of y is just the inner product between this shifted input and discrete sinusoid with frequency k, because that's the frequency that where we're computing the DFT. And what happens here is that taking an inner product of the shifted signal with a sinusoid is exactly the same as taking an inner product of the signal times a shifted sinusoid, because we're doing just convolutional shifts. So the idea is that if you have x and a sinusoid, okay, and you're taking the inner product between these two guys, if you shift x and you take the inner product, because we have circular convolutions, this is exactly the same as shifting the sinusoid in the opposite direction. Okay, should check that you're convinced by that. Actually, we're shifting the sinusoid in the opposite direction. Okay, so we're shifting it in this direction. Okay, this is what that means. Now we know that shifting the sinusoid is just scaling it by a single number that depends on the frequency k, sure, but it's a single number. So that single number can just come out. So essentially, when we shift a signal, here we get the DFT coefficient at k again. We're just weighting the Fourier coefficients by a constant that depends on their frequency. This makes a lot of sense, right? Because the DFT essentially, if you think about it, when you're doing the DFT, you're saying, okay, this signal x that I have, it's actually equal to x of, let's say, 1 times the frequency with the sinusoid with frequency 1 plus x of 2 times the frequency of the sinusoid of frequency 2, and so on, right? This is what the DFT basically means. You're expressing your signal in terms of these sinusoids and you're weighting each of them by the DFT coefficient. So now, if we shift this guy, what are we doing? We're just shifting each of these sinusoids, right? This is exactly equivalent because this guy is equal to this linear combination of the sinusoids. We're just shifting them. And if shifting them just produces this term, okay, this term here, that depends on the frequency each time, well, in your new representation, you still have the frequencies with the same frequency, and now you have just modified the Fourier coefficients. Okay? So basically, when you apply translation to a signal, what happens is you're just multiplying its Fourier coefficients by a certain constant that is this complex exponential that depends on the frequency. That's all you're doing. Okay, and that constant actually has a very simple form. It has the frequency here, the shift here, and here, and that's it. Okay? Okay, so finally, we're in a place where we can analyze convolution in the frequency domain. So the situation is we have that y is equal to the convolution of x1 and x2. And now we're interested in what happens. So we've already seen what happens to y, like how you compute y in the time domain if you want, or in the spatial domain if you're thinking about images, where it's equal to just shifting one of the images and then taking an inner product with the other one. Okay? Now we want to understand what is happening in the frequency domain. And for that, we're just going to compute the kth DFT coefficient of the convolved, the result of the convolution. And that's just inner product with the discrete sinusoid of frequency k. So we write this thing out. Remember that convolution is basically you shift one of the signals and you take inner product with the other one. Okay, that's what we do. So now we're going to express this shifted signal as its in terms of its DFT components. Okay, so this is exactly what I was doing before in this picture here, where basically what I'm doing here is I'm saying, okay, you can actually express this guy as the Fourier coefficient of the shifted signal times the corresponding. Okay, this is exactly equal to x to the s. Okay, this is because this is what we do when we compute the DFT. Oh, and I need to put a 1 over m. Okay, so remember that as is basically you apply the inverse DFT to the DFT coefficients of x. We actually end up with, sorry, of shifted x, you end up with shifted x. So we now know that those coefficients are just equal to this constant times the Fourier coefficients of x2, okay, because realize that we're talking about x2 here. Okay, so basically this blue term has been replaced by its DFT representation. Why have we done that? Because now what we can do is we can basically take out this sum, and now the DFT of y can be written in terms of this guy, okay, the DFT coefficient of x2 times this inner product between the discrete sinusoids psi j and psi k, and this expression where we're, sorry, actually I said something wrong. We're taking out this sum, okay, the sum over j, it's coming out. And now we're taking the sum of x1 s against only this term, because no other term depends on s, okay? So we have rearranged things so that the kth DFT coefficient of y is equal to the sum of the jth coefficient of x2 times this inner product and times this term. And the cool thing is that this term is basically just the jth DFT coefficient of x1. And this follows from the fact that we have expressed x2 in terms of its DFT decomposition, and this term shows up because we're shifting x2. So now when we compute what this sum is equal to, turns out that this sum is equal to the jth coefficient of x1. So to keep track of this guy is expanded into this, and then we regroup all of this stuff, and it just realized that it's equal to the jth DFT coefficient of x1. I realize that this derivation is pretty complicated and you should just go over it slowly on your own, but the result is extremely powerful, so it's worth it. I have tried to make it easier for you by color coding it in this way. So the blue thing is equal to the blue thing, the red thing is equal to the red thing. And now we end up with this sum from j is equal to 0 to n minus 1. But if you think about this inner product, this is an inner product between orthogonal functions. So there are going to, this inner product is always 0 unless j is equal to k, and in that case it's equal to n. So we end up with this spectacular result, which is that if you convolve signals in the time domain, what's happening in frequency is something super simple. Their Fourier coefficients are just being multiplied. We have proved this for the DFT, but you can essentially prove the same thing for the Fourier series if you're doing convolution in continuous time. This is a bit out of the scope of the course because of, we have limited time, but the ideas are very, very similar. In general, if you convolve two signals in time, what's happening in the frequency domain is that their Fourier coefficients are just being multiplied. And this is all because of how sinusoids, what happens to sinusoids when you translate. Okay, it's not completely obvious, but because of that, we have this term that appears here, and because of that, this just becomes the DFT coefficient of x1. Okay, so it's worth saying again, if y is equal to x1 convolved by x2, then the DFT coefficient of y is equal to the product of the DFT coefficients of x1 and x2. The reason why we need circular shifts that wrap around, is so that this is true. Because otherwise it's no longer true that when you just shift the sinusoids, they stay sinusoids with the same frequency, because you would have border effects if the sinusoid disappears on one side. These border effects, again, are really annoying. We have to deal with them when we're dealing with real data, but don't get too distracted by them. The reality is that when you do, most of the time you can just deal with them. So when you're doing convolution in time, even if you don't necessarily have circular shifts, you can use padding and other stuff to represent this as multiplication in frequency. And this is a really, really powerful way of thinking about convolution as multiplication in frequency, because then you can just imagine how the signals look in the frequency domain, and it's very easy to understand why certain things are going on. And I'm going to give you an example in a moment. The exact same result applies for images when we're dealing with 2D images, or 2D signals in general. If you have a convolution between two 2D signals, in frequency what's happening is that the 2D DFT coefficients are being multiplied. Okay, so if you want to compute the convolution between x and y, what you could do is you can take the DFT of x, that looks like that, this sinc function that we had discussed, and you consider the second signal, and you also compute the DFT of the second signal, and what you do is you multiply them together. Okay, this product looks like that, and now you can just take the inverse DFT, and boom, you get your convolved result. In this case, I have to tell you, maybe it's more because of the very simple structure of the signals in the time domain. It's probably simpler to think of this as just a convolution in the time domain, but to see the true power of the result that we have just proved, let's look at this situation where we have the image and it was blurred, so these local averages happen. When we think of the image in the frequency domain, this is what we see. Okay, it has a very complex frequency structure, but the cool thing is that when we think of the filter that we're convolving the image with when we blur, in the frequency domain, this filter has a very simple structure where essentially it's a low-pass filter. So in the high frequencies, so these are the high frequencies, its value is much lower than in the low frequencies. So we're just doing pointwise multiplication of the DFT of the image with this filter when we're applying a convolution, when blurring is occurring. So that's all that happens. Basically, the low frequencies are preserved and the high frequencies are suppressed. And when we suppress the high frequencies, we lose resolution. So this result allows us to understand very intuitively what is happening when we convolve with a blurring kernel. So basically, we have reached this conclusion that if we have a linear translation invariant model, essentially what we're doing is we're convolving the input with this impulse response. And now we have realized that convolving with the impulse response is just multiplying by the Fourier coefficients of the impulse response. So essentially the only thing we're doing is we're scaling the Fourier coefficients of the input. That's all we're doing when we're applying a linear translation invariant function to a signal. The DFT of the impulse response with which we're multiplying the DFT of the signal is called the transfer function. For any LTI function, if we're applying the LTI function to x, this is exactly equivalent to just taking, this is the DFT representation of x, we're just taking the DFT coefficients of x and applying this and weighting each of them. Okay? By the way, here we have forgotten that we have to do 1 over n here. Okay? But well, that's just a constant. Don't worry too much about it. The important thing is that we're weighting the DFT coefficients. That's all we're doing when we're applying a linear translation invariant function. And this, in retrospect, may or may not seem obvious, but it's quite interesting, right? We started with a very simple assumption on the model that we want to apply. If the input is shifted, then the output should also be shifted. And we end up with an interesting conclusion, which is if we make that assumption and the model is linear, then at the end of the day, all we're going to do is we're going to scale the Fourier coefficients. Why is that? Because essentially of what I said before, maybe I'll repeat this reasoning. You have a signal x, you're essentially expressing it in terms of sums of weighted sinusoids with different frequencies. If you have a model where if you shift this guy, you are only shifting these guys. What happens when you only shift these guys is that they just get multiplied by a certain coefficient. So because of that, you're constraining your model to just weight the Fourier coefficients. If you do anything else, then your model is actually going to be translation variant. It's going to vary when you translate the input. Okay, so what have we learned? For high dimensional signals, fitting linear models is intractable. Assuming translation invariance yields efficient models and is quite reasonable for a wide range of signals. When we do that, when we assume translation invariance for a model, then what happens is that applying the model is essentially just convolving the data with an impulse response. In addition, we have realized that when we do convolution in the time domain or in the spatial domain, that's equivalent to multiplying or computing a pointwise product in the frequency domain. So this means that linear translation invariant models scale each Fourier coefficient in the data individually. Okay, that's equivalent. Constraining your model to just scale each Fourier coefficient in data individually is exactly equivalent to constraining your model to being linear translation invariant. Thank you very much.